In this video, we'll translate from our sketched versions of the solutions to our spring system to a much more accurate simulation. What I want you to keep in mind as you're watching this, though, is the translation of what we saw in the qualitative sense. So on the first time interval from 0 to pi, we would get a damped oscillation. And then as soon as we reach pi, we're going to get some combination of a forced-driven function that has constant amplitude, as well as the exponential decay. Let's move to MATLAB and we'll see how that plays out. So here's our scenario. We've got a spring that's displaced up from its equilibrium and we're about to let it go. So we see is exactly what we'd expect is oscillations, but they're quite quickly damped out. And then we kick on the external force once time reaches pi, or 3.14 seconds. And here we have the force constantly driving over time. It's not fading. We just keep reapplying this green line force. And what we see fairly quickly is that the mass and the force seem to get in sync. And we see that on the right-hand side with the graph of the solution. We're going to run that again to see a little more detail. Keep in mind you have the time visible up here as well as the magnitude of the external force. We have t equals pi marked clearly on the solution graph over here. So here again we've moved the mass up to here, 1 meter away from its natural equilibrium, and then we let it go. What we see in the simulation is that this damping is quite high, so the oscillations fade away very quickly until we start reapplying the force, the regular force that's going up and down and oscillating as well after t equals pi. Let's watch that one more time. Again, holding steady, and then letting go. What I'd like to draw your attention now is how quickly this initial oscillation fades. It takes about 2-3 seconds. And when you look at the right-hand side of the graph here, after t equals pi, when the forcing function's on, what you see from about here on in is that the oscillations are of a constant magnitude. It's not true right at the beginning. We notice we have a smaller amplitude and then a larger, and then they're roughly constant. So what we have in this domain here is a combination of the steady amplitude cosines sines and the exponentially decaying ones. But the exponential decay is the same as e to the minus 2t. It's the same on this end as it is on this end, and so we see that the time to be not so visible anymore of around 2 seconds also applies here. After about time 5, 6, the oscillations are basically those of the steady state, and the exponentially scaled ones, the e to the minus 2t cosines, aren't visible, don't play a major role in the actual simulation or predicted motion of the mass. So that's the simulation result, a very quantitative presentation of what our functions look like. If you can tie those back to what we saw in terms of the functions, then you're making great headway in terms of connecting the ideas with the actual quantitative predictions we're making.